What if a visitor from another star system is about to make its move right in our own backyard? On October 29th, the third known interstellar object, 3I Atlas, will slingshot around our sun at a staggering 68 kilometers per second. This single moment could finally answer the question everyone is afraid to ask. Is it just a rock, or is it a probe under intelligent control? The data is coming in, and the theories are flying. So let's delve into what we know and what comes next.
The critical moment.
So why does this one date, October 29th, matter more than anything else? This is the moment of perihelion, the object's closest and fastest point in its journey past the sun. At this instant, the laws of physics offer the greatest possible advantage for any change in trajectory. If 3I Atlas is just a comet, it will follow a predictable path dictated by gravity. But if it's something more, this is the most fuel-efficient moment to fire an engine and alter its course. For years, astronomers like Avi Loeb of Harvard University have urged the scientific community to consider the possibility that interstellar objects could be technological, arguing that we must be open to extraordinary evidence. This perihelion pass is the first real test. Every telescope that can get a clear view will be watching as it emerges from the sun's glare, looking for the slightest deviation from its gravity-defined path. We have seen comets exhibit non-gravitational forces before, but those are from outgassing, and they are typically gentle and chaotic. A sharp, deliberate change right at perihelion would be a different beast entirely. This isn't just another flyby, it's a critical junction that could validate or dismiss years of speculation in a matter of days.
Goes 19, limitations.
You may have seen images online, supposedly from the GOES-19 satellite, tracking the object as it nears the sun. But here's the reality check. Is a weather satellite truly the key to unlocking this mystery? GOES-19 is a marvel of engineering, but it was designed to watch Earth's weather, not faint objects in deep space. According to NOAA scientists like Dr. Dan Lindsay, the satellite's primary tools are optimized for tracking hurricanes and solar flares. They simply lack the sensitivity and the specific plate scale needed to resolve a dim magnitude 12 object against the blinding glare of the sun. The signal-to-noise ratio is fundamentally too low. To get a usable position, you need a meticulous process of astrometric calibration, correcting for the satellite's motion and optical distortion against a catalog of background stars. This is incredibly difficult when your instrument is built to look down at clouds, not up at the cosmos. A dedicated space telescope like Hubble or Webb is designed to stare at a fixed point for hours, gathering every photon, while GOES-19 is built for rapid, wide-angle scans of a moving planet. While the idea of using it is tempting because of its unique viewpoint, no peer-reviewed study has confirmed a successful detection. The real data will come later, from instruments actually built for this kind of work.
Debunking the rumors.
With an event this significant, misinformation is spreading faster than the object itself. Social media is flooded with claims of secret engine burns, doctored images, and supposed proof of alien intent. However, the International Astronomical Union's Minor Planet Center, the official body for this, has stated there is no confirmed evidence of any anomalous activity from 3I Atlas. Experts like Dr. Matthew Holman, a former director of the Minor Planet Center, consistently emphasize that scientific conclusions must be based on reproducible data, not blurry videos. The process of confirming a trajectory change is rigorous, requiring raw, time-stamped data and an error analysis that accounts for everything from camera noise to cosmic rays. Most viral claims use artifacts, hot pixels, or simple projection errors. People are falling victim to confirmation bias, seeing what they want to believe in random noise. The scientific standard requires that any claimed detection must be independently verified by multiple observers using different equipment, until the object re-emerges from behind the sun and professional observatories gather that new high-precision data. All talk, of course, changes, is pure speculation.
The Oberth effect.
Now, let's talk about the physics that makes the perihelion pass so critical. There's a principle in astronautics that can turn the sun's gravity into a cosmic supercharger, and it's called the Oberth effect. First described in the 1920s by the brilliant German physicist Hermann Oberth, one of the founding fathers of rocketry, it's a concept that mission planners live by. Here's the simple version. Firing an engine when a spacecraft is already moving at its maximum speed provides a much bigger boost in energy than firing it at a slow speed. Kinetic energy increases with the square of velocity. As 3I Atlas dives toward the Sun, it accelerates to its peak speed of nearly 70 km/s. If it were to fire an engine at that exact moment, the effect would be magnified enormously. We see this principle in action with real missions like NASA's Parker Solar Probe, which repeatedly dives close to the Sun to use the Oberth effect during its gravity, assists at Venus to shape its orbit. A relatively small burn could radically alter its outbound path, sending 3I Atlas toward a completely new destination. That same burn, performed out in the cold of deep space, would barely nudge it, making Perihelion the most efficient place in the entire solar system to change course.
Astrometry math.
So how will scientists actually prove a maneuver has happened? It's not about seeing a flare, it's about the cold, hard math of astrometry. Astrometry is the science of measuring the precise positions of objects in the sky against a background of fixed stars. Every observation is time-stamped, calibrated, and checked for errors. The data is then compared to a predicted path, or ephemeris, calculated based on the laws of gravity. Missions like the European Space Agency's Gaia satellite have revolutionized this field. As Gaia project scientist Dr. Timo Prosti explains, Gaia has created an unprecedentedly precise 3D map of over 1 billion stars, providing the perfect reference frame for this kind of work. When 3I Atlas reappears, astronomers will use this star catalog to pinpoint its location with arc-second precision. They will plot its position inside an uncertainty envelope, a cone of possible locations. A natural object will stay within that cone, but a maneuvered object will demonstrably break out of it. It's a process that requires patience, as multiple observatories around the world must confirm the same deviation to rule out localized errors. This collaborative cross-checking is the bedrock of astronomical discovery.
Delta V detection.
Let's get into the specifics. What exactly are astronomers looking for? The key metric is called delta V, which simply means the change in velocity. At perihelion, even a tiny delta V can have huge consequences down the line. According to orbital dynamics experts like Dr. David Farnokia at NASA's Jet Propulsion Laboratory, a burn of just 1 km per second would cause the object's position in the sky to diverge from its predicted path by about 20 arcseconds by the time it nears Jupiter's orbit in March 2026. For context, that's a gap that well-equipped telescopes can easily detect, provided they can measure positions with an accuracy better than 5 arcseconds. A larger burn is even easier to spot. A 3 km per second maneuver would create a gap of over an arc-minute, and a 7 km per second burn would pull the comet several arc-minutes away from its natural course. The timeline is critical. This divergence isn't instant but grows steadily over the weeks and months following the perihelion pass, making a consistent observation campaign in late 2025 absolutely essential. This is the objective yardstick. There are no blurry JPEGs or subjective interpretations here. If 3I Atlas fires an engine, the evidence will be a precise, repeatable, and undeniable shift in its position in the sky.
Why skip Earth?
If this object is an intelligent probe, many people assume its destination must be Earth, but from a purely strategic standpoint, that makes almost no sense. Why would an advanced visitor ignore easier targets and head straight for the most complicated one? Earth has a deep gravity well, meaning it takes enormous energy to land, take off, or even enter orbit. Furthermore, as NASA's planetary defense officer Dr. Lindley N. Johnson can attest, our planet is under constant surveillance. We have a global network of military and scientific sensors designed to detect incoming objects. Any unexpected arrival would trigger an immediate planet-wide response, what some have called a planetary immune system. An intelligent probe wouldn't seek confrontation. It would seek resources and a safe place to operate without alerting the locals. It already passed Mars earlier this month with no sign of slowing down. A direct approach to Earth would be the strategic equivalent of announcing your arrival to a potentially hostile and unpredictable civilization. The logical move for a visitor isn't to knock on the front door of the most heavily defended house on the block, but to go somewhere quieter and less defended.
The Jupiter option.
If not Earth, then where? The data points to a far more strategic destination, the Jupiter system. If 3I Atlas performs a maneuver at perihelion, its new trajectory will be revealed as it heads outward. The next major milestone on its path is a close approach to Jupiter, on March 16, 2026. coming within 54 million kilometers. For an intelligent probe, this is the perfect destination. Jupiter is surrounded by a kingdom of moons, many of which are packed with the raw materials needed for refueling, repairs, or even building a long-term base. It's a resource-rich environment far from the prying eyes of Earth. Scientists who study our solar system's architecture, like Dr. Scott Shepard of the Carnegie Institution for Science, understand that the outer solar system is where the real wealth lies. The moons of Jupiter are perfect for in-situ resource utilization, the concept of living off the land in space. Furthermore, Jupiter's own immense gravity can be used for additional gravity assist maneuvers to reach other targets in the solar system with minimal fuel. The Jupiter system isn't just a collection of moons, it's a self-contained empire of resources, making it the most logical target for any interstellar traveler.
Ganymede resources.
Let's focus on the crown jewel of the Jupiter system, Ganymede. What makes this moon so special? It's the largest moon in our solar system, even bigger than the planet Mercury, and it offers a unique combination of resources perfect for an advanced technological presence. As astrobiologists, like Dr. Kevin Hand at JPL have detailed, Ganymede is believed to have a massive subsurface ocean containing more water than all of Earth's oceans combined. That water ice on its surface can be easily harvested and converted into hydrogen and oxygen, rocket fuel. On top of that, Ganymede is the only moon known to have its own magnetic field, which offers vital protection from Jupiter's intense radiation belts. Its gravity is just a fraction of Earth's, making it easy to land and launch spacecraft. Its thick ice shell, potentially kilometers deep, also provides excellent shielding from micrometeorites and cosmic radiation, making it an ideal place to build a protected, long-term base. It's the perfect combination: a gas station, a radiation shield, and a low-gravity construction yard all in one place, an unmatched piece of real estate in the outer solar system.
Barnard's Starlink.
Finally, where did this object even come from? While its interstellar origin is confirmed, its home star system remains a mystery. However, astronomers have noted a tantalizing coincidence. The object's incoming trajectory, or radiant, points back to the general direction of Barnard's star. Located just 6 light-years away, Barnard's star is one of our closest stellar neighbors. In 2018, a team led by astronomer Dr. Ignacy Ribas announced the potential discovery of a super-Earth exoplanet orbiting the star. The link to 3I Atlas is purely speculative, of course. A journey from there, even at 60 kilometers per second, would have taken 10,000 years, a mind-bogglingly long time that pushes the limits of what we consider possible for a technological probe. The alignment could be nothing more than a cosmic coincidence, which is statistically the most likely answer. But it remains a fascinating thought experiment that keeps astronomers intrigued. For now, the probability that 3I Atlas is anything other than a natural object remains very low, but the coming months will provide the data needed to start answering these incredible questions. So, here we are, at a rare observational threshold. On October 29th, 3I Atlas makes its closest pass to the Sun. The data we have so far shows a natural object following a predictable path, but physics tells us this is the single best moment for a controlled maneuver. When it re-emerges from the Sun's glare in November, the world's telescopes will be waiting to see if its path has changed. A continued natural trajectory means it will head out of our solar system, but a sharp, unexplained turn toward Jupiter would change everything. What happens next will be measured, not imagined. Thanks for joining us on Space Facts. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the cosmos. Thanks for watching InnoVision Tech.